This is part 1 of section 4.4, and I just want to do a little review of where we are. 4.1 was finding the antiderivative of integrals like 3x squared dx with an indefinite integral. So we added 1 to the exponent, divided by the new exponent, and remembered to include plus a constant because it just gave us a family of possible original functions that when we took the derivative of them, their answer was 3x squared. And then in section 4.2, we seem to totally do away with that and worked on geometry. We were finding the area under a curve using rectangles of equal width, and we had to do a lot of geometry, base times height. In section 4.3, we talked about the definite integral notation. So it was similar to the integral from 4.1, except there were little numbers on the top and the bottom. And what that stood for was finding the area under a curve from the left bound to the right bound. And we found the area using geometry first when we were talking about the definite integral notation. And then secondly, we talked about a limit definition for finding the area under a curve using an infinite number of rectangles. And Riemann's sums was that method where we found area under a curve using rectangles of different widths sometimes or similar, same widths. But there was a big formula for finding the area under a curve using the limit as n approaches infinity and the summation of rectangles from 1 to n, and then the function with the b minus a over n times I plugged into it, and then that times b minus a over n, which was the width of each rectangle. So how do these things have anything to do with each other? Why are they all in the same chapter? And why that integral notation? Why is it the same for 4.1 and 4.3 with a definite integral? What ties them all together? Well, let's see if you can figure it out. In section 4.1, we found the integral of x dx. And that equals, remember, you add 1 to the exponent and divide by the new exponent, and then put plus c on the end. So that's going to be x squared over 2 plus c. All right, that was section 4.1. Then in section 4.3, we added these numbers 1 and 4, and we found the definite integral, or we called this the definite integral, and all we were doing was finding the area. So what this says is find the area of the function y equals x, which is graphed over here. 0, 0 is the x and y intercept, and then it goes up 1 over 1, up 1 over 1. So this point is 4, 4. And we're going from 1 to 4. So this region, where x equals 1, to this region, where x equals 4. We're trying to find the area of that region. Well, it's not exactly a triangle, but you can use it. You can find the area using the triangle formula by finding the area of this whole big triangle and then subtracting the area of this little triangle. So 1/2 base times height. The base of this whole big triangle from 0, 0 to 4, 0 to 4, 4 is 1/2 4 times 4. It's 1/2 the base, which is 4, times the height, which is 4. And then subtract the area of the little triangle. 1/2 times the base is 1 and the height's 1. So that area would be 8. 1/2 4 times 4 is 8 minus 1/2, and that's 7.5. So that's the area of this. Now we can only find the area of that using geometry so far. But why is there this integral notation? Somehow there must be some connection between those two. So let's look at it. If we've got this formula, that's the integral of x, which is x squared over 2. So I've rewritten it down here. Is there anything we can do with these numbers 4 and 1 and this answer? I've just ignored the c for now. We'll talk about that later. Do you see anything we can do with the numbers 4 and 1 and this formula to somehow get this idea going on here, to get this answer of 7.5? Well, what if we plug the 4 in here? What do you get? 4 squared over 2. Right? What is that? That's 8. And then what if we plug the 1 into this? That's 1 squared over 2. And then we subtract them. What do you get? 8 minus a half, there's 7.5. That is amazing, I think. That is called the fundamental theorem of calculus. Woohoo! It was one of the huge, big discoveries in calculus. If a function is continuous in a closed interval from a to b, and some new function, we'll call it capital F, is the antiderivative of that function on a to b, closed interval, then the definite integral from a to b of that function is the answer you get when you do the antiderivative of f. So little f was the derivative, and you figure out what the original function was. They call that capital F. And you plug b into that antiderivative. And then you plug a into that antiderivative, and you subtract the two. That is the area under the curve from a to b without having to do the big limit formula with the limit as n approaches infinity, with the sigma from 1 to n of the function times the width. Yay, way easier, right? Because we know how to do antiderivatives. We spent a whole section on that. So now all we're doing is plugging numbers in and subtracting the two. Huge, huge. All right, let's practice. Evaluate each definite integral using the fundamental theorem of calculus. Hold up a second. Why do we need this if we could just do this using geometry, right? Well, obviously not every function makes a nice geometric shape. So finding the area under the curve is not so easy as finding the area under a straight line. So that's why we need this fundamental theorem of calculus. All right, so integral. Definite integral, because it has numbers here, from 2 to 5 of 2x. So this is a straight line. We're finding the area under the curve 2x, which is a straight line, from 2 to 5. So the antiderivative, add 1 to the exponent, divide by the new exponent. So adding 1 gives you x squared, and then this 2 and this 2 would cancel. So we're going to cancel those out. And then here's our plus c. Now this is the new thing. This notation here shows that you are going to plug in 2 into x and 5 into x, not in that order. We're going to plug 5 in first, plug in the upper bound first, and then the lower bound. And then we'll see what happens with the c. But this bracket here, you can use a bracket, or you could even just use a straight line if you want. Excuse me. So you plug in the 5 first, you get 5 squared, and that's 25, plus some constant, and then minus. Remember we're subtracting this whole function, so we use parentheses. Plug in the 2, you get 2 squared, plus c. Now, that's 25, right? And that's 4, and we're going to subtract them. But what happens with the c's? If we distribute this negative, it's going to be c minus c. So the c's are just going to cancel out. So this c and this c are just going to cancel out. So from now on, we can remember that the c's are always going to cancel out. So when we do the definite integral, we don't have to remember c. So for definite integrals, you do not need the plus c on the end. And that's why when you do indefinite integrals, you may forget the plus c. But don't leave c behind on indefinite integrals. Definite integrals, you definitely need them. So we've got 25 minus 4, so the area under the curve of 2x from 2 to 5 is 21. Let's do another example. The integral from 0 to 2 of x squared plus 1. Add 1 to the exponent and divide by the new exponent. So the antiderivative of x squared is x cubed over 3. Integral of 1 is x. So always integrate first. Do not plug any numbers in until after you've integrated. And then here's our notation showing that we are going to plug in the 0 and the 2. Plug in the top number first. 2 cubed plus 3. Now remember to plug the 2 into both of these places. A common error is to plug the 2 into here and then the 0 into the second place. No, you plug 2 into the whole antiderivative, so that's that. Then you plug 0 into the whole antiderivative, and that gives you that. So this is 8/3 plus 2. When you add those together, you get 14/3, and this is 0, so we're not really subtracting anything. I know that looks like that 0 is the exponent of that, but it's really part of the antiderivative up here. All right, so let's do a trig one. Antiderivative of 2t is t squared. You add 1 to the exponent and divide by the new exponent. That's how those 2's cancel. And the antiderivative of cosine is positive sine. We're integrating that from negative pi over 2 to pi over 2. So first you plug in the pi over 2. So you're going to have pi over 2 squared. And plug in the pi over 2 here, and you get sine of pi over 2. Pi over 2 squared is pi over 4. Pi squared over 4. Oh, I suppose I should do this part first. Plug in the negative pi over 2 here. So we get negative pi over 2 squared and sine of negative pi over 2. So pi over 2 squared is pi squared over 4. The sine of pi over 2 using your unit circle is 1. And then minus, and we're going to subtract this whole thing right here. So when you square this, it's positive pi squared over 4. Can't really see that on the bottom there, can you? And then the sine of negative pi over 2 is negative 1, but if we subtract a negative 1, that's why this turns into a plus 1. So remember to distribute that negative there. So we've got pi squared over 4 plus 1 minus pi squared over 4 plus 1. So the pi squareds over 4 cancel, and we have 1 plus 1 left, so our final answer is 2. What if we have an absolute value? We want the integral from 0 to 3 of an absolute value function, x minus 1. I just showed the picture here to remind you, but you don't have to graph it. You do have to figure out where the absolute value equals 0, because you want to know where the slope changes, where the function line changes. Because we're finding the area from 0 to 1, and then from 1 to 3. We're going to break up the integral. So set up your absolute value inside, set it equal to 0, and find out where that point is of your absolute value. And we're going to break up the integral, or the absolute value, into 2 integrals. And remember, integrals just stand for area under a curve, so you can break it up into 2 different regions and find the area of the 2 regions and add those up. So from 0 to 1, this part right here, the slope of that line is actually negative 1, and the y-intercept is positive 1. So if you just put a negative around this x minus 1, negative times the x minus 1, that's the equation of this line here. And then from 1 to 3, the line is just the x minus 1 that we started with. So remember, absolute value actually is a 2-part, it's like a piecewise function. So break it up into those 2 pieces. And integrate from 0 to 1, and then integrate from 1 to 3. So the integral of this, add 1 to the exponent here and divide by the new exponent, gives you x squared over 2. Antiderivative of 1 is 1. I mean x, sorry. We still have the negative out in front here, and we're integrating from 0 to 1. Antiderivative of x is x squared over 2. Antiderivative of 1 is x. Integrating from 1 to 3. This one has no negative in front. So now we plug in the 1 into both places here, and then we're going to plug in the 0 into both places and subtract those 2. So we'll have negative 1/2 minus 1, and then 0 minus 0. And it's a plus because we're subtracting the negative here. Here we're going to plug in the 3, so 3 squared is 9, so we have 9 halves. And plug in the 3 here, so there's our 3. Minus, then plug in the 1. 1 squared over 2 is 1/2, and then minus the 1. So calculating each of these, 1/2 minus 1 is negative 1/2, but there's a negative out in front, so it's going to be positive 1/2. And that's 0. 9 halves minus 3, that would be 6 halves, so 9 halves minus 6 halves is 3 halves. Minus 1/2 minus 1. 1/2 minus 1 is negative 1/2, so we're adding 1/2. So we have 3 halves plus 1/2, that's 4 halves, which is 2. So we have 1/2 from this part, and this is 2. So 1/2 plus 2 is 5 halves, or 2.5. That's the area of this region from 0 to 1 plus this region from 1 to 3. So it's the area under the curve. There's your homework. Page 293, 1 to 43 odd. Have a great day.